Good evening, and welcome to the New England Aquarium and the Simons IMAX Theatre. And this is the 4th annual John Carlson Lecture, which we present in partnership with the Lorenz-Center at MIT. My name is Nigella Hilgarth, and I am the President and CEO here at the New England Aquarium. Just think for a moment, we're all here this evening sharing a very special moment in a special place that really I consider the hub of the universe. And by that, I don't just mean the theater. I mean that we are on a planet that has life. And as far as we know, it's the only planet in our universe that has life. There may be other planets, but this is the only one that we can be certain about that. And we know that the ocean plays a very big role in making sure that this planet actually can have life. And I think that most of us are here tonight because we share an interest not only in the world's oceans, but a great interest in how the oceans influence systems like the climate system that influences our lives so much. And we know that so many of our activities, such as burning fossil fuels, including coal, oil, and natural gas, release carbon dioxide into the atmosphere. And as I'm sure all of you know, that carbon dioxide acts like a blanket, it traps heat, and it's warming the earth and the oceans, and that leads to disruption to many systems. So that sounds very simple, but of course, actually understanding and predicting change on a global scale is enormously complex, and it involves many different scientific disciplines. And so bringing the best scientific minds together to study the science of climate change is the focus of the Lorenz-Center at MIT, and you will hear a bit more about that in a moment. The Lorenz-Center and the Aquarium share a desire to communicate climate science to the public and to raise the level of public understanding and the attention to the issues of global change. Information, I believe, comes more meaningful as we discuss it and we consider how to use it to shape our lives. So I very much hope that tonight's presentation about the history of our climate and planet will lead you to new discussions about your interests and concerns with your family, your friends, and your colleagues. And I think by having discussions, you will help to share good information and raise awareness and attention, which is what we need to happen. And I want to thank MIT's Lorenz-Center for making the Simon IMAX Theatre the home of the John Carlson Lecture. We're very proud about that. And now I'd like to welcome Kerry Emanuel, the Cecil and Ida Green Professor of Atmospheric Science, and Dan Rothman, Professor of Geophysics, who will also take your questions at the end of the talk. So please come to the podium.
Thank you. Well, good evening. I'm Kerry Emanuel, and my colleague Dan Rothman and I direct MIT's Lorenz-Center. We'd like to begin by thanking Nigella Hilgarth for her very generous welcome. Thank you for that. And indeed, the whole aquarium for hosting this 4th annual John Carlson Lecture. This is the annual public outreach lecture of the Lorenz-Center, which is a climate think tank at MIT. Our mission is to bring scientists together to conduct basic research into climate. Our goal is to attract the most talented physicists, chemists, biologists, and mathematicians into the field to address one of the most complex scientific problems we face today. We extend special thanks to John Carlson for his very generous support of this lecture series, and thank you all for coming this evening. I want to extend a special welcome to MIT alumni, faculty, and students. We know there are many of you in the audience, and also to all students and teachers who are here tonight. And now it's my great pleasure and privilege to introduce tonight's speaker, Peter-Molnar, Professor of Geological Sciences at the University of Colorado at Boulder, and Fellow at the Cooperative Institute for Research in Environmental Sciences, also in Boulder, Colorado. Peter has made so many contributions to different areas of geophysics that just to begin to list them would devour a considerable portion of his lecture time. But it's probably safe to say that he's best known for helping to figure out what happens when the giant plates that make up the Earth's crust collide and how that process builds mountain ranges. He is the recipient of many awards, most recently the highly prestigious Crawford Prize, awarded annually by the Royal Swedish Academy of Sciences, who cited him, quote, for his groundbreaking contribution to the understanding of global tectonics, in particular the deformation of continents and the structure and evolution of mountain ranges, as well as the impact of tectonic processes on ocean atmosphere circulation and climate. You can see that the Royal Academy is not above terrible punning with the groundbreaking research. It's especially fitting that the first recipient of this award, the Crawford Prize, in geophysics was Edward Lorenz, after whom our center was named. On a personal note, I first met Peter in the mid-70s when I was an undergraduate student at MIT. I was looking for a faculty advisor, and his research really appealed to me, even though I was working on atmospheres and not rocks. So I asked him to be my advisor, and he looked puzzled and said he didn't know much about atmospheres. I think I may have said that we could fix that problem. And we did, and since then we've ended up publishing a few papers together. You're about to hear a lecture by one of the great geophysicists of our time, who also happens to be a terrific guy. Enjoy.
Well, thank you, Nigella. Thank you, Kerry. I once introduced Kerry, and he did just as good. I did just as good a job at embarrassing him as he has with me, because he really exaggerated on that. And John, thank you very much for giving me this opportunity to take on a challenge that I've never had. I've never given a talk like this in my life. So challenges are what make life fun, so I'll go for it. Okay, first let me state what the overarching problem that motivates me here tonight. You'll see that I don't answer this question. I don't really get that close to it, but one always should have a big problem in mind. And that question is this working? I can't, oh, it is just barely. Well, I'll just read. What geological processes transformed the Earth's climate from without ice ages, without much ice on Canada, between 300 and 3 million years ago to another with recurring ice ages every 40,000 years or so since approximately 3 million years ago. This is the overarching question. Now I'm going to step back and look at a much smaller question and give you starting 2 facts. First, about 300 million years ago with little ice on Canada, then after that, 2.7 million years ago, thick, huge ice sheets began to wax and wane over the whole of Canada. And what do we mean by that? I'm going to show you an animation made by Tanya Atwater at the University of California in Santa Barbara. And what you'll see, I'll show you this twice, but what you'll see is ice building up in Canada, spreading out over, the United States is down in here, spreading out over this region. Sea level drops, so you don't see Cape Cod over in here, you don't really see the Aleutians, and then it retreats back. Let me show you this again. Note that sea level drops, you put a lot of ice onto Canada, so you take it out of the ocean, you spread out over a huge area, ice building up, starting someplace up in here, we don't really know, spreading down into North America, deep into North America, into the United States, and then retreating back. This has happened roughly 50 times in the past 2.7 million years. Many, many times. We are in an interglacial at the present time. Okay, the second fact, about 2.7 million years ago, large mammals crossed from south to north and north to south America in what's called the Great American Biotic Interchange. And just 2 examples. From North America, in North America, cats evolved. They did not evolve in South America. They evolved in North America, and 2.7 million years ago or so, they moved into South America. This is another cat that's gone extinct, in fact, called Smilodon. It exists in both South and North America eventually. I think it's kind of a pun, Smilodon. This was a saber-toothed cat, and I don't think when the name was given it had anything to do with a smile. In the other direction, predecessors to armadillos, the Glyptodon, evolved in South America, evolved over a long period, and eventually moved into North America to become the armadillo. Going both ways, they had to cross through Panama, through the Isthmus of Panama, to get there, which explains the title of this talk. Now, there's an interpretation that's very common, as you'll see, that goes with this. The Isthmus of Panama emerged 2.7 million years ago and enabled those animals to cross the isthmus while it blocked water from the Pacific from entering the Atlantic, and thereby it facilitated ice ages, facilitated those recurring features that I mentioned. Well, why do geologists think an emergence of Panama would cause an ice age? What's underlying this? So what do you do when you don't know the answer and you've got your computer? You go to the web and you go to Wikipedia, right? And you look it up. There's Panama over in here, and you read what it says. And I'm going to blow up this paragraph, and I'll tell you in advance that a small fraction of you is cringing at the moment in reading this, and maybe a large fraction will cringe at the end of this talk. The isthmus was formed some 3 million years ago during the Pliocene epoch. This major geologic event separated the Atlantic and the Pacific Oceans and caused the creation of the Gulf Stream. I haven't heard any groans, but I know they're taking place. Okay, why do people think that? Well, I'm going to show you a couple of calculations run with a numerical model of ocean circulation. What's plotted, the colors are showing the strength of circulation increasing downward. So this bright red in here, 50 centimeters a second, that's of the order of 20 inches a second, if you like. It's quite, did I do that mathematics right? 20 inches a second. Somewhat slower in here, coming up North America, South America, coming through here. This is calculated with a closed seaway through here. Now, when they do this calculation with an open seaway, nothing changes out in here very much. You might have noticed a weakening in this area. That's a bit of a change in this part of the world. Let me just go back. That's with it closed. That's with it's open. The presumption is earlier it was open. If you look at the difference between them, as I said, you don't see anything in the Pacific. This is the difference between open minus closed. So the arrows are pointing back that way. The logic would go forward in time, going forward in time would say that when you close this, this would strengthen in some way. This is a calculation. This, though, is believed to be important in heating up the northern hemisphere, and, or I should say, the closing is important in, it turns out, in making ice ages possible. Now, why do they think this? What's the underlying part of this? So here's a map: Mexico, Central America, Panama, South America. This is a map of salinity. Salinity is the quantitative way of measuring how salty the water is. And this is colored so that you can see it's much different in the Atlantic. 36 parts per thousand. 36 parts per thousand is 3.6%. On the Atlantic Caribbean side, 34 parts per thousand, 3.4%. The difference is only 0.2% in the salinity. And I suspect that even an expert French chef in a 3-star restaurant in France could not taste the difference between these two. Perhaps I'm wrong. But this is a big difference in the ocean. You just have to trust me, that's a big difference. So the Atlantic is more saline than the Pacific. Saline means saltier, but it also makes the water denser. So that water is dense, it's more prone to sinking, at least eventually. So what's the underlying hypothesis? When Pacific waters were blocked, water in the Caribbean will become saltier. It became saltier. Then the salty water will cool as cold air passes over it in the North Atlantic. So up in this area, cold air coming across North America towards Europe will cool that water. Cold water is more dense than warmer water. Salty water is more dense. The combination makes the water really dense. And so that cold, salty water will sink into the deeper ocean and be part of what is in some places called thermohaline circulation. Thermo from temperature. Haline is a synonym for saline. It's how much salt is in the water. So there is a community that uses that particular term. Okay, well, let's keep going. What do the textbooks say? Okay, and let me warn you, the textbooks agree that the emergence of the Isthmus of Panama is essential, but they disagree about how it actually had an effect. So let's take one. This is actually two textbooks. Stanley's textbook. This is a revised edition, but the same figure and everything are copied in this later one. And first, let's just read this. The uplift of the Isthmus of Panama may have triggered an ice age by elevating the salinity in the Atlantic waters, by the arguments I've given you, causing them to sink north of Iceland, as they do today. That's the water going northward. This change would have deprived the Arctic Ocean of heat from the Atlantic. So in the picture, you have water moving through the Caribbean northward, and then it's saline water, and it becomes cold, so it sinks near Iceland up in here. North America, Greenland, Europe over here. And it doesn't reach the Arctic. Whereas Stanley and Prothero and Dott would argue when you had an opening in here, you had fresher water. That fresher water would continue northward all the way into the Arctic. It's not as saline, it's not as dense, so you have to cool it more, and it would get into the Arctic, and it would keep that Arctic water warm, so you wouldn't have ice up there. Well, let's look at another textbook. Rudderman, Bill Rudderman. Bill Rudderman is an outstanding paleoclimatologist. First, read the words. Several climate scientists have hypothesized that this strengthened northward flow of warm, salty water would have suppressed the formation of sea ice. Salty water requires the temperature to be lower to become ice than fresh water. So if it's saltier, it won't make ice quite so easily. The reduced cover of sea ice would have made more moisture available to nearby land masses and triggered the growth of ice sheets. And he's appealing again to this northward motion, northward flow, but he's saying that when you get up around Iceland, you wouldn't make sea ice because the water has become saline and you have to cool it more in order to make ice. One last one. Steve Marshak's book, again an elementary textbook. As warm water moves up the Atlantic coast, it generates warm, moisture-laden air that provides a source for the snow that falls over New England, eastern Canada, and Greenland. In other words, until the Gulf Stream was diverted northward by the growth of Panama, there was no source of moisture to make abundant snow and ice. And I think you all are trying to imagine a huge ocean out there, the North Atlantic, that is not a source of moisture. That's what he says. So let me just back up. The textbooks agree closing the Central American Seaway, emergence of the Isthmus of Panama, was necessary for the ice ages. But one says so that ice could form in the Arctic. That's Stanley and Prothero and Dott. Another says so that ice could not form in the North Atlantic and moisture becomes available. And the third, so that more moisture in the overlying atmosphere could move northward. They don't agree, right? Not much doubt about that. So the textbooks disagree about how the emergence of Isthmus of Panama facilitated ice ages. And I would contend that when the textbooks disagree, there's an opportunity for exploration. There's a problem out there. People, at least some people, don't seem to understand well what's happening. So let's back up. What do we know with confidence? Well, how do we know that ice ages began 2.7 million years ago and that ice sheets expanded over Canada since that time? The first kind of fact comes from moraines. I'm going to give you only a subset of the possible information. But here's a sketch, mountainous terrain, a glacier. This is a glacier that has flowed down valley, down in this area. Glaciers excavate rock, they carry it along, they transport it. When they get to the end, a glacier reaches its limit. It leaves all that behind in a terminal moraine. It carries material along the edge called a lateral moraine. This glacier expanded to here, retreated, left a moraine in here, and now the glacier is retreated back to there. And a good example, this is a photograph from New Zealand, the Southern Alps up in here. You see a glacier coming down this valley. Well, these trees are on a ridge way out of here in the front of the basin that wraps all the way around. These trees and that ridge are a moraine left by that glacier when it flowed much further out here some 10 or 20,000 years ago. Seeing moraines that have been left by continental glaciers is a little harder, but you actually have them quite a bit around near here. Here's Boston, here's Cape Cod, Nantucket, Martha's Vineyard, Long Island. These islands are moraines, mostly moraines, left by the last ice sheet. Glaciers came down here, piled up rock on Nantucket, Martha's Vineyard, Long Island. As they retreated, they left rock on Cape Cod and other places. So these moraines, these are the last glacial expanse, the last big glacier on Canada, so these aren't the first, but this is the kind of evidence that we can use. A second, Oxygen isotopes in foraminifera. Foraminifera are kind of plankton. You all know that whales eat plankton. These, the ones I'm going to show you actually, are near the bottom of the ocean. But this is a small microorganism. And I'll come back and explain this figure again a bit more. But what's plotted here is going back in time, the present 1, 2, 3, 4, 5 million years ago, and a measure of the amount of the oxygen 18, the isotope of oxygen 18 in these foraminifera that have been accumulated on the floor of the ocean. And you see that number increasing. But you can think of this as a thermometer. Warmer, cooler down here, coming down this way. We are up here where it's relatively warm. The last glacial advance was way down here. The previous interglacial is way up there, and so forth. All of those oscillations are due to that. Now, how does this work? Oxygen has 8 protons and 8 electrons, 8 protons in the nucleus, 8 electrons outside. Most oxygen has 8 neutrons in its nucleus. The sum of 8 and 8 is 16, so we call this oxygen 16. A small fraction of oxygen has 10 neutrons in its nucleus, so this is oxygen 18. In fact, there's a smaller fraction still that has 9 neutrons in its oxygen 17. But let's not worry about it. Oxygen 18 with 10 neutrons in here. Why is that important? Well, I'm going to make an analogy between the energy in these molecules and just jiggling around. Molecules vibrate continuously. Warmer molecules vibrate faster than cooler ones. Many processes, like melting of solids and evaporation of liquids, depend on how rapidly the molecules vibrate, essentially how warm they are. We all know that. You heat up something, it's more likely to, if it's a solid, it will become a liquid. If it's a liquid, it might evaporate. Okay, this is the key. More massive isotopes, like oxygen 18, vibrate more slowly than less massive isotopes, like oxygen 16, when they're at the same temperature. And an analogy might be the Boston Celtics. The little guys move a lot faster than the big guys, but they all sweat the same amount. They're all at the same temperature. It's just the big ones vibrate a bit more slowly. And this is key. Therefore, the more massive isotope, oxygen 18, evaporates less readily than the lighter isotope, oxygen 16, at the same temperature. So, a simple picture. Ordinarily, as you have today, you evaporate water from the ocean. Preferentially, the oxygen 16 goes into the vapor and then ultimately into the clouds. Eventually these clouds move, or the vapor moves over the land, you have rain, it runs back. So there's an equilibrium. The atmosphere has less oxygen 18, more oxygen 16 than the ocean. But then what happens when you get an ice age? The same evaporation takes oxygen 16 preferentially out of the ocean and leaves oxygen 18 behind in the ocean, moves over, precipitates out, but you trap it in this ice. So you accumulate in the ice an enrichment of oxygen 16, a depletion of oxygen 18, and conversely, in the ocean, you wind up during an ice age with an enrichment in oxygen 18 and a depletion in oxygen 16. So, oxygen isotopes and temperature. During ice ages, the ocean becomes enriched in oxygen 18. That's what I just told you. Also, as temperature decreases, the foraminifera, the plankton, use a larger fraction of oxygen 18. So, when it's cold and ice sheets form, the foraminifera, the plankton, become enriched in oxygen 18. And that's the picture that you see here. This is a measure of the fraction of oxygen 18 that the foraminifera have. You see it increasing downward. That's a symptom of it becoming colder, and also ice ages. As I said, this is the present, the last ice age, the penultimate interglacial period, the penultimate glaciation, and so forth, back and forth. Okay, the third part, ice-rafted debris. Glaciers carry a lot of debris. This is a glacier. You see the ice, people for scale. All over the top, lots of debris, layers of ice with debris inside them. They carry a lot of debris. When they get out into the ocean, they carry debris out to sea. This is debris on an iceberg. But icebergs, it's like death and taxes. There's some inevitability here. Icebergs melt. They'll always melt. So the iceberg will carry its debris, go out into the ocean, and suddenly it melts. The debris doesn't float. It sinks to the bottom, and you accumulate this debris, this ice-rafted debris. It's carried by the rafts of ice that go out there. So a work of Kira Lawrence, going back in time 1, 2, 3, 4 million years ago, Don't worry about the green. The red is temperature. 20 Celsius is 68 degrees C, 10 is 50. You see this cooling over this period as we go towards the present, cooling towards an ice age. But more importantly, look at the magnetic susceptibility, which is a gimmick for measuring how much ice-rafted debris is there. All of a sudden, at that time, 2.7 million years ago, there's an abrupt increase in this. This is the ice-rafted debris, abruptly beginning 2.7 million years ago. So I go back to this. We know that glaciers have expanded on the continents because of the moraines that we see out there. We know that many ice ages have occurred because of the variations in the oxygen isotopes in the foraminifera. And we know when the first one came because of this ice-rafted debris. And I should say, there's still more information in this. I'm not telling you everything. We're pretty sure that the ice ages began roughly 2.7 million years ago. Okay, the Great American Biotic Interchange. At this time, before roughly 2.7 million years ago, the continents, the mammal fauna on the two continents was very separate from one another. In the southern hemisphere, we have this thing called the glyptodon, porcupines, which made it to North America, sloths. Our sloths don't look like this. Anteaters, opossums. Opossums, you may know, are marsupials. Marsupials were a dominant fauna in South America at this time. Even predators were marsupials. In the northern hemisphere, we had bear, mastodons, which look like elephants, big cats, cougars or pumas, camelids, camel-like animals, and others. There were horses, there were dog-like animals in North America at this time. And then abruptly, around 2.7 million years ago, these animals crossed each direction. And we know when they were there because we can date, I say we, of course, I'm not the one who does this, but geologists can date sediments and they can find fossils of these and they can identify these fossils. Well, let's focus on one, the glyptodon, to start with, over here. The glyptodon moved into North America and became the armadillo. Picture of an armadillo, this one from Central Florida. This is the size of a small dog or a cat. The glyptodon is gone. It lived until fairly recently. It was done in by humans. A drawing made by an artist back a long time ago, judging by when he lives, shows a sketch of a glyptodon and Native Americans hunting this beast. This guy is huge. The glyptodon next to the armadillo, and I should say Darwin found these when he was working in I think it was Argentina. The glyptodon weighed 2,000 kilograms, that's 2 tons. This is the size of a small car, the size of a Volkswagen, but much heavier than a Volkswagen. This is a huge, huge animal. And now we have the armadillo in North America. Let's look at the sloths. Sloths are another one. These, you don't recognize these as sloths except if you look at the teeth down in here. You all know what sloths look like. They can come with 2 toes. They can come with 3 toes. They're slow-moving, sleepy animals that live in the trees. Back before, well, this painting was meant to represent 12 million years ago. You had ground sloths living down here. You can see the toes on these that are quite distinctive. By the way, that's a predator marsupial, in fact, about the size of a dog. These animals got to be very large. Here's a photograph in the museum in Bogota, Colombia. My colleague Hector Mora here for scale. This is the giant sloth. This was a huge animal at that time. For scale, here we are, giant sloth and an elephant, a huge animal that was roaming around, and this has evolved into these guys in North America. This is what we have now. Before 2.7 million years ago, actually the sloth may have crossed a little earlier, but essentially until 2.7 million years ago, there were hardly any sloths in North America. And then, of course, the cat. Oh, no, sorry, from North America. From North America to South America, camelids. This is a word that means camel-like animals. You don't ordinarily think of camels in North America. We don't have camels, but there's plenty of fossil evidence for camels living in North America until sometime since 2.7 million years ago. They got into South America. Now we have llamas. Llamas are camel-like animals. Alpaca, another one. There are 4 different species of camel-like animals in South America. These didn't get here until 2.7 million years ago. Before that, none of these animals were there. And finally, the big cats. The big cats, the cougar or the puma. This animal evolved in North America. It didn't get to South America until 2.7 million years ago. When it got there, it had a feast. It found lots to eat, and it feasted royally on this. To what extent the decimation of the South American mammal fauna was due to their being eaten by animals like this, and to what extent it was because they were displaced by other animals that just could fill the niche, I don't know. But the expert on this, or an expert on this, David Webb, shown here, fully half of the modern South American mammal genera gained a foothold there and evolved there in less than 3 million years. So South America and the big animal life, the big mammals, they changed by more than half just in 3 million years because of this crossing. Okay, so we go back to this history shown here. The first big Laurentide ice sheet, the first big ice sheet on Canada was at 2.7 million years ago. The Great American Biotic Interchange at 2.7 million years ago, essentially simultaneously. Is this a coincidence? Repeat this, first big ice sheet, Great American Biotic Interchange. Is this a coincidence? Is it cause and effect? Is it due to the emergence of Panama? Well, let's take a look at the modern. This is the Pan American Highway. You can start in Alaska and come south through, start on the north coast of Alaska, come south through Alaska, through Canada, back into the United States, through Mexico, make your way all the way down to Panama. But then there's a problem. There's a little gap. It's called the Darien Gap. There's a place where the road ends. You start in Ushuaia, in southern Argentina, you can make your way north all the way up. You get there, but there's a gap. There's no road. You can't get across. You can try. You can bring a vehicle. You can get across. But it takes a bit of imagination. Sometimes you have to do it a different way. The landscape is a bit rough. Topography is steep. And as I said, there is no road. You're going through quite a mess. And I can tell you with confidence, a lot of them don't make it. Just don't get through at all. And you might think, well, the problem is it's excuse me, Nigella, but it's a Land Rover. You know, maybe the problem is they had the wrong vehicle. So you can come in with a bigger vehicle, and this has been done too. They've tried to put railroads in here and send trains through, but it just hasn't worked. This region still doesn't have a road. It's now well into the 21st century, and it doesn't have a road. Well, if it's so hard to cross the Darien Gap, who did cross Central America in the Great American Biotic Interchange? Again, back to David Webb. I'll read this. A rough ecological analysis of the Inter-American mingled fauna shows that it was broadly based and predominantly savanna adapted. At least 2/3 of the known Inter-American mingled fauna was a diversified savanna fauna. Woodland savannas and thorn forests that were seasonally arid formed the principal avenue for the exchange. Well, what's a savanna? This is a plot now, a month. This would be January, February, March, April, May, and so forth. That would be December. Monthly precipitation on that axis. Boston, not much variability. Monthly precipitation of 100 millimeters, that's about 4 inches. Almost every month is the same. Boston is not a savanna. I think we all know that. Boston, and it gets an annual rain of about 40 inches, at that much. In Panama today, there is a seasonal cycle. There's a dry period. But most of the time, pretty intense rain, 2,600 millimeters, that's 100 inches, 8 feet a year. That's a lot more than you get in Boston. What, 2.5 times what you get in Boston. And Nairobi, Kenya, this is a classic savanna. Mostly low rainfall, but 40% occurs in 2 months, in April and May, and more than 50% includes in April, May, and June at this time. And who lives in a savanna? Savanna adapted animals crossed. Well, who lives there? Well, these guys live there. These guys live there. And zebras and cheetahs and leopards, a bunch of animals that like living out in the grasslands without many trees. But I ask you, if you grew up in a savanna, would you go here? With all these snakes and mosquitoes, and if you're a giraffe and branches all around you, would you go here? Or more precisely, when would you go here? That's the question. Okay, introduce you to Dolores Piperno. In late Pleistocene, Ice Age time, Panama was arid. You had savanna vegetation. This particular part of Panama, this, I'm not going to pronounce it, this watershed, 3,800 millimeters at that time. That's, I'm not going to, it's 150 inches a year, so 12 feet or so a year. Per annum today, during the late glacial period, under 1,000 meters, much less rainfall. This place over in here, late Pleistocene, the lake was dry and savannah-like vegetation expanded at the expense of the tropical deciduous forest, the modern potential vegetation. So, if you grew up in a savanna, when would you go there? The answer is obvious. You'd do it during an ice age. That's the ideal time. You wouldn't have to contend with most of the obstacles that are there, although the animals that are there probably would remain an obstacle. And preferably during a big ice age. Okay, well, this is a map showing a sketch of the last glacial maximum, Laurentide ice sheet, covering Canada, reaching into North America down in here, reaching down to Cape Cod over in here. The first big ice sheet, the first recorded advance of the Laurentide ice sheet, reached 39 north, way down here, way down to St. Louis. This is the Mississippi River, that's the Missouri River, St. Louis lies in here. The first big one was the most extensive of all of them. So, is this a coincidence? The first very big ice sheet at 2.7 million years, the Great American Biotic Interchange also at that time, savanna-dwelling animals crossed in the Great American Biotic Interchange, and during a big ice age, during big ice ages, Panama becomes a savanna. You know, do we need to have the Isthmus of Panama emerge at 2.7 million years? All we need are ice ages to allow those animals to go back and forth. And in fact, the vertebrate paleontologists like David Webb and Lawrence Marshall and others have known this or have inferred this for some time. This is a map of South America with the present day distribution of savannas. Their guess at 3 to 2.7, a bigger distribution, but notice they stretch it into Panama. Back before that time, a very similar distribution, but not in here, and they have an opening there. They're just assuming that. And then back earlier, not as much in the way of savannas in this region. Well, an obvious question poses itself. Did other animals pass through the Darien Gap when savanna dwellers did not? Okay, well, the boa constrictor, yeah, sure. Boa constrictors had crossed from South America to western Panama by 19.3 million years ago. The argument that's given by those who think the Isthmus of Panama emerged is, well, they can wrap around a tree, as this guy has, and float across. A log will carry them across, and they'll go from one side to the other. The Bushmaster viper, it went the other direction, North America to South America. We estimate that the Central and South American forms diverged 18 to 6 million years ago. So this means that there was a way for them to get across or to separate from one another, in this case from North America into South America, at least by 6 and perhaps 18 million years ago. Salamanders, a particular salamander, in this case, a divergence time between the faunas of South and Central America of over 18 million years. Well, the argument would be, oh, well, it's an amphibian. It can swim, for one thing. Plus, it could get on a leaf or on a log, and it could cross. Sure. And then finally, the Tungara frog. This is a frog. This is all swelled up. He's about to call his potential spouse and let her know that he's eager. This guy invaded Middle America from South America 6 to 10 million years ago. So you can ask the question, if you were a boa constrictor or a bushmaster snake, a salamander, a Tungara frog, or just about any frog, when would you go here? I would argue that's a stupid question. If you were a boa constrictor or a bushmaster snake or a salamander or a Tungara frog, why would you leave the Darien Gap? This is home. This is paradise. You wouldn't go away. The only reason you'd leave is if there got to be too many of you and you'd expand out. So the logic, I would argue, the logic that the fact that these guys could cross and others couldn't doesn't demonstrate in any way that the Isthmus of Panama emerged at this time. Okay, where do we stand? Ice ages began 2.7 million years ago. Savanna-dwelling animals crossed the Darien Gap in the Great American Biotic Interchange approximately 2.7 million years ago. During an ice age, Panama becomes a savanna, but jungle-loving amphibians crossed the Darien Gap well before 2.7 million years ago. Well, recently, geologists have been getting at this. I cite the work of Camilo Montes, a Colombian geologist who's been working in Panama for some time. And he I'm not going to go into the details of this, but he would argue that 25 million years ago, indeed, there was a gap over here. But by 15 million years ago, there was no gap. You could go all the way across. The rock in this part of Panama and South America had become glued together by this time. And he has a bunch of arguments for this. So this is the present configuration. This differs from that mostly because you've bent Panama into its arcuate shape. But we've had an isthmus there for quite some time. So we go back to two facts. After 300 million years with little ice on Canada, 2.7 million years ago, huge thick ice sheets began to wax and wane over the whole of Canada. Also, 2.7 million years ago, large mammals crossed from north to south and south to North America in the Great American Biotic Interchange. And we have this interpretation. The Isthmus of Panama emerged 2.7 million years ago, enabled those animals to cross the isthmus while it blocked water from the Pacific from entering the Atlantic and thereby facilitating the ice ages. We can reject this. This has no foundation that one needs, one can see. Well, what did happen? Let's go back, and this is just a very brief summary. Again, we're looking at that same oxygen isotope curve, increasing, warmer up here, cooler down here, 1, 2, 3, 4, 5 million years ago. Oxygen isotopes increase when it gets cooler. And we've focused on this 2.7 million years ago. I neglected to point out earlier, actually, that if I were to show you this curve without that red arrow and ask you when was the first ice age, you might say here, way down there, because after this, this is a big oxygen isotope signal down here. Or you might say here, why wasn't it here? What happened at this time? Well, we know that it's that time for other reasons, and we can see there's a big positive signal in the oxygen isotopes. But if we smooth through this, if we just take this curve and smooth through with a 200,000 year Gaussian window, we just smooth through this curve, smooth through all of these oscillations to get this nice simple red curve as it comes down, what do you see? The oxygen isotopes show slow cooling. And then northern ice sheets begin at roughly 2.7 million years ago. So you're cooling slowly down to here, and then suddenly at this point, ice builds up in Canada. And virtually all of you live in Boston, so you know that if the temperature goes from 40 degrees Fahrenheit to 25 degrees Fahrenheit, as it gets cooler, maybe you put a bit more clothes on, but you don't change your life until it crosses 32 degrees, when the ground freezes. And when the ground freezes, you go from driving your car in one way to driving your car another way. You go from walking a little bit more carefully when it's colder because you might slip on the ice. That temperature where you suddenly can freeze is a rather crucial moment. And what do we have here? Well, finally, at this time, 2.7 million years ago, you could build up enough ice in Canada. Canada became cool enough that you could keep ice there long enough to build an ice sheet. And this is George Philander, one of the giants of physical oceanography and tropical climate, likes to say ice is really incidental to the ice ages. And that's his point, that you've had a long cooling, and then you get this event where you get ice, but that's deceiving us. The focus really should be on this gradual cooling. We should be focusing on the slow cooling, and this is just the same as when you suddenly get ice on the streets and on the sidewalks of Boston. This is the more important phenomenon, and that's the question I'm not answering is why did that happen? But look at this as a gradual cooling, and therefore a slow transition from no northern hemisphere ice sheets until 2.7 years, when recurring ice sheets could abruptly begin to wax and wane. So, conclusions. The Earth cooled slowly for several million years. Finally, 2.7 million years ago, ice could and did accumulate on Canada in the first of recurring ice ages. When the northern hemisphere cooled, Panama became a savanna, briefly, just for the ice age time. The savanna environment in Panama enabled the Great American Biotic Interchange. So that really poses the question, did the emergence of Panama, of the Isthmus of Panama, whenever it occurred, and I would argue this is probably closer to 20 million years ago than 3 million years ago, have anything to do with ice ages? And obviously, you can tell that I think it had nothing to do with it. Now, I was told that this talk would be partly for high school students, and so I have to put some lessons in. First lesson, when something doesn't make sense, like the emergence of the Isthmus of Panama as a cause of ice ages, the approach should be to challenge the assumptions. Go back to what's been assumed right back to the beginning. Ask the right question. Science is about asking questions. The most important part in some ways of science is to ask the right question. So a good question, who, the answer is savannah dwellers, crossed the Darien Gap 2.7 million years ago. A not so good question is, how did the others cross the imagined Central American Seaway? Instead of focusing on trying to explain away those that crossed at that time, don't worry about them. And finally, obviously, don't believe everything that you read. And that's in the textbooks, and you know all this, the Wikipedia, et cetera. And as I think you can all see, I have not demonstrated that the Isthmus of Panama did not emerge 2.7 million years ago. I've just shown that it need not have emerged. So let's tack on a little bit to the end. Don't believe everything that you hear either. Thank you. I think I have to turn this off, Dan, if you're going to talk into that.
It's okay. Go ahead. I know Peter will be very happy to answer.
Turn that on.
Oh, okay.
You want to stand next to me?
It's on. It's on. I know Peter will be very happy to answer any questions, so I encourage you to ask.
So my question is, so the ice ages started happening, but what caused them to cause there to be multiple ice ages? Why didn't it just come and stay?
Good question. The standard view, yes, why did we have ice ages begin at some time and why didn't it stay that way? Why did we have oscillations in ice ages? The prevailing view, which I think makes a lot of sense, has to do with the Earth's orbit, two parts of the Earth's orbit. First, if the sun is here, this is exaggerated, that would be a circular orbit, but the Earth actually has an eccentric orbit. I think I'll skip that, the importance of that. The second, as you know, the axis of rotation is tilted so that the Earth spins around a North Pole, but the North Pole, the sun, relative to the sun, the axis is tilted. That's why we have seasons. That tilt varies back and forth. Not by a lot, you can see by a couple of degrees. But what that means is that sometimes the northern hemisphere is tilted towards the sun a little bit more, sometimes a little bit less. Now, how do you make an ice sheet? You make an ice sheet by not melting last winter's snow. And how do you melt last winter's snow? Well, have a hot summer. So when you're tilted down, the summers are a little bit warmer and you can melt last winter's snow. When it tilts back the other way, you can keep some of that snow and you go back and forth. This oscillation in obliquity has a period of about 40,000 years, 41,000 years. So just that tilting, it's remarkable that that little bit would work. But it seems to. There's no question that the data show a 41,000-year period. So this is the simple explanation. Thank you for asking a question I was prepared to answer.
There.
The long-term gradual cooling of the Earth that you showed, your average time plot, any conjecture on what's causing that?
So the question is about the long-term average cooling and what might have caused it.
Yes. This is a much more speculative answer, okay? And long-term average cooling, maybe I deceived you a little bit by being quick with that. But just quickly, this is what happens during El Nino. You all hear about El Nino. During El Nino, the Eastern Pacific becomes warm, and Canada becomes warm as well. That's a well-observed phenomenon, not every single time, but commonly observed. Canada becomes warm. So just thinking about that, if warm Canada is associated with a warm Eastern tropical Pacific, how did it look in the past? This is sea surface temperature, the normal situation where it's warm in the west, cool in the east. This is sea surface temperature during a big El Nino, warm in the east. I'm going to show you results from a drill core over here. This again, Kira Lawrence's work with Junghui Liu and Tim Herbert. Just look at the red curve. This is inferred sea surface temperature at a site in the eastern part of the Pacific, and you see steady cooling, 1, 2, 3, 4, 5 million years ago. sea surface temperature going down, don't worry about the oscillations. The simple pattern would be a cooling across that region. And to put that in map view, that site is over here. That's the cooling. And the point is today, it's cool out in here. Out here at this time, at the present, back 4 or 5 million years ago, it was warmer by quite a bit and may have been more El Nino-like. And then with that, it's called a teleconnection, with that connection to Canada, you would have had a warmer Canada back at 4 million years ago. I hasten to emphasize that that's kind of my dream explanation, and I could back it up more strongly than I have right here. But there are plenty of people who think this is nonsense. So you're free to doubt me.
Another question? Yes, back there.
Isn't there any direct tectonic or geologic evidence for the emergence of the isthmus? Maybe plate tectonic reconstructions, fossils, whatever?
So the question is about the direct plate tectonic or other geologic evidence for the emergence of Panama?
If you reconstruct back, well, let me just let me emphasize a point. Work of Bruce McFadden. They recently widened the canal. They dug up a lot of rocks, so they found a whole lot of stuff they hadn't found. What they've found in here is that the local fauna is striking because it's composed entirely of North American mammalian taxa. So here you're Panama, that's South America right over there. All the animals at 20 million years ago looked like North America. So the important piece is just this little piece over here. That's the important part of Panama. Then I have to, where do I go? I go the other way. This is Camilo Montez's work. This is a distribution of some of that rock today. This volcanic rock in here, volcanic rock wrapped around against South America. So the coast of South America comes in here, that's Panama. Then the coast of South America is over here, comes up, and that's Panama up in here. So you have a continuous belt that comes across, and when you reconstruct back in time, 25 million years ago, you straighten all of that out, but you don't pull back quite so far. And I could take this further, I'll just show you a picture without explaining it. What he's done, this guy's a really clever guy. What he's done is he's looked at sediment in various places, and what he finds is actually it's the next one. What he finds is that the sediment in this basin looked like it came from Panama, if it's younger than 15 million years. If it's older than 20, it doesn't look like Panama. And this sediment is carried by rivers, but one thing we know that rock and sediment cannot do is swim across the ocean. Rocks don't swim. So the only way for that rock to get there is for rivers to have crossed in and brought that sediment in. So there are a bunch of arguments that are pinning it down. And the tectonic evolution, yes, you folded up rock in here, but that rock, that's sedimentary rock that was derived from eroded rock that was above sea level. So I don't think there's a reason to think you've built Panama recently in geologic time. I do have an answer to one question left, I think, in here, if someone wants to guess what that question.
Oh, question.
So your argument for why we should believe that oxygen-18 isotopes pertain to sea surface temperature is about the precipitation of ice on the continents. But you're using that argument for a time before there was a lot of ice in the continents. So why should I believe you?
Yeah,
so the question, which will be easy to summarize, is why should Peter be believed?
I'm not the person to answer that question. It's a good question, and I cheated on you. The oxygen isotopes, there's two parts to them. One is that they're preferentially, they go into the vapor when you evaporate. The second part is that the organisms themselves preferentially take oxygen-18 into them when it's cold. When it's warm, it was in the middle of a slide and I probably went too fast. But when it's warm, they don't. So when it's warm, they take oxygen-16 and oxygen-18 equally well. And the explanation for this, I think, is a tough one. It's a tough one to explain. And I know that because I'm not sure I understand it myself. And I think it's actually rooted in quantum mechanics. It's one of these processes that's well observed, nobody doubts it. Each organism is different. So you can't take one plankton and measure something and another plankton and measure it and compare them, because they have different processes that take in the oxygen 18, and hence different temperature dependencies. I don't have a slide for that, but thank you.
More questions? Oh, I'm sorry. I keep on ignoring this stuff. Yes, please.
It's kind of a general question, but I'm just curious with, as long as the period is for something like geophysics, do you have any sort of smaller natural systems where you're able to run experiments to test some of these hypotheses on, you know, like a, just I guess something where you can directly measure an impact when you compare, you know, scenario A and scenario B, because obviously with 40,000 years, you don't really have an opportunity to take a second look.
So the question, I might say, is excellent, and his questioner is asking whether we can perform experiments in such lines of work.
That is a good question. And the definition of a good question is one that the speaker can't answer.
You must be prepared.
He asked a good question. I could hide and say one can run computer simulations, but one has to believe an awful lot when one has to make a lot of assumptions for them. So in principle, one can do that. And indeed, when you put a big ice sheet on Canada, you do displace the belts of rainfall south. So it's easy to believe that you would make Panama drier at that time. I've tried actually to see if people find that, but they always cut the maps off further east. They're looking at the Atlantic and northern South America. So I don't know for sure that they, doing that, have found it. And I wouldn't be so distrustful of that work simply because they weren't attacking that problem. They didn't have a bias that's off in the corner of whatever they've done. So that's one way to do it. Well, we do know where savanna-dwelling animals live, so that part I don't think we need to test. You can ask, was that the key, making it a savanna, or could have some predecessor gone through? A biologist would have to answer that. I couldn't do that.
Question.
Thank you. I'll have to think about that. Don't email me too soon. I need to sleep a bit before I can think up an answer for that.
So there was one back there, right? Oh, there. No? There.
Were there a parallel series of ice ages in the southern continent, around the South Pole?
Well,
so the question is, were there a parallel series of ice ages in the south?
No, that's a good question too. There's been ice on Antarctica for almost 30 million years, or 32 million years, I think, in fact. There's been a lot of ice on Antarctica. East Antarctica, the big part in the eastern hemisphere, has had ice since then. The western hemisphere, the ice seems to have accumulated more recently. Whether there have been advances and retreats like this, I don't think so. And the reason is simply that the ice reaches out to the continental margin. It doesn't have land to go out into. So if you make more ice, you just make more icebergs, but you'll never see more ice there because it just goes out and fills up the Southern Ocean with icebergs. And I think that, I don't know whether they see cycles of icebergs. That's a good question. I should think about that. It's not, yeah.
The reason I was thinking about it is I was wondering what was motivating these animals to move in both directions.
Question is, what motivated the animals?
I don't know. Actually, I have never thought about that either. I suppose that animals, even large mammals that haven't developed the way humans have, might be curious, and some space opens up, and why not go look at it? I mean, if I were one of them, I'd do that.
It was inexpensive real estate, just like today. I'd like to move on to other people. And in particular, I noticed there's some high school and middle school students in the audience, and I'd really like to encourage one or more of them to ask a question before we take a question from the back. It's your chance.
I understand.
I know where you are.
Went.
Yeah, I never would have either, but you know, it's my job to ask. There you go.
Ah,
Do you think maybe it was because of population? Like the population was a lot, so to spread out more resources and stuff?
I can imagine that they were, so the question is, was it possible that it was population, that were just too many of these animals in a space and they wanted to?
Maybe not just too many, maybe there's just more stuff, so it's like you have to share more if you're in more like space with population, but so there's more space and resources.
Oh, she's got a good idea, I think. So is it possible that these animals had to share resources and maybe the populations grew too large and they just had to find more space? I think that's a good idea. I think it's hard to test because the paleontologists can find fossil animals, but it's very hard for them to know how many were there. Of course, the fossils are rare. Most animals that die don't become fossils, they become destroyed. So figuring out how big that population was, I think, is a challenge. But it's a challenge that maybe paleontologists should figure out how to study and how to attack. I'm not a paleontologist, so I'm not going to do it, but that's a good idea.
I just have one more very small question. I saw that there was I think they were called mastodons. Was that the name? And they looked like elephants, and they were in the Americas. I just wondered, why they're in Africa.
Well, mastodons are a particular kind of elephant-like animal, and they were particularly widespread, they were renowned during Ice Age time. They're not quite elephants. They're thought to have had a lot of fur. Mammoths and mastodons, I'm not sure quite the difference, but they're very similar to one another. So there were elephant-like creatures, but they weren't quite elephants, and they were in North America. They crossed, got to South America, and they were destroyed, as I understand, by humans. Humans crossed into North America and South America only 12 or 15,000 years ago, very recently, and they were devastating. Most of what's disappeared is the consequence of humans. Early humans, Native Americans long before modern Native Americans even came in. But mastodons are like elephants, but they're not exactly the same, and they came in.
Thank you. There's a gentleman in the back who's been very politely waiting.
Well, the fluorocarbons, they're gaseous molecules. Actually, I talked with a colleague yesterday, and they see these in the ocean. They can see these having come into the ocean, and then not so much after the Montreal treaties. So they see them in the ocean, but I don't think they've settled to the bottom. How they would get to the bottom of the ocean isn't clear because they're not just going to sink. They dissolve in the seawater, and then they're moved by the water. But they're not going to go to the bottom. And do I study them? No, that's chemistry, and I don't study chemistry.
Cherokee, the western part of Panama, spent lots of time there.
Mm-hmm.
The Pacific side. I've noticed things are getting hotter every year.
I don't think that's the fluorocarbons. That's interesting because it's widely thought that the tropics warm much more slowly than the high latitudes. High latitudes, the Eskimos, one of my colleagues used to go to Alaska, and he said he asked the Eskimos if it was getting warmer, and he said, oh, the Eskimos in northern Siberia said, oh yeah, even the Russians can hunt in winter now up there. So the warming is much more more marked at the high latitudes. So this is a bit of a surprise.
Are there any other questions? I'd like to ask one if I can take a minute. Did the Darien Gap pose any problems that we can see for the initial southward migration of humans?
That's a really good question, and it's interesting. I don't think it's dated well when humans went through, but Dolores Piperno's work is actually late glacial. It's about the time when humans would have gone through. So it's entirely possible that had humans evolved a little faster, back a little bit earlier, they wouldn't have gotten to South America because they'd be too soon. So I don't think, I don't know, but I can imagine that yes, the last glacial period, the effect of it reached recently enough to allow humans to cross.
So one quick question, then we have to end.
Were the continents Europe and Asia affected by the ice ages, and if so, how?
Question is if Europe and Asia were affected by the ice ages.
Oh yeah, during the ice ages, the whole world got colder. Even the tropics, as much as 5 degrees C, 9 degrees Fahrenheit, the tropics are thought to have become colder. Asia became very dry and very cold, Eastern Asia. You wouldn't want to be in Beijing in the spring because the dust would be probably overwhelming at that time. So the whole globe was affected by ice ages. I'm just focusing on this one region where it had an impact on the animals.
Okay, I'd like to close by thanking the New England Aquarium for making this event possible here, and especially I think the speaker deserves one more round of applause for an outstanding talk. Thank you very much.